So in the previous part lecture, we discussed that the 2D camera calibration process to compute the camera matrix K results in computing homography between sets of planar points across two different planes. That is the points, the 2D points in the world coordinate system and their corresponding image coordinate on the image plane, which is the 2D plane. So in the previous power lecture, we discussed that computing homography results in the following optimization problem. Minimize norm of ax squared, relative norm squared, subject to constraint that norm of x, relative norm squared of x is equal to 1. The optimization problem of the form occurs in many other applications as well. It just happens that the homography also results into solving this mathematical optimization problem. So since solving this optimization problem is of interest on its own, we will take this topic independently of the camera calibration topic. So we will discuss how we can use a singular value decomposition to solve the following mathematical optimization problem, and then we will come back to the homography to compute the camera matrix K. So over here we assume that the matrix A is of dimension m cross n. So it's an m cross n real matrix where m is greater than n, greater than or equal to n, and x is an n-dimensional real vector. So from the basic linear algebra, we know that the singular value decomposition of matrix A, so A is an m cross n matrix, and the singular value decomposition or SVD in short of matrix A is given by A is equal to U sigma V transpose, where U is a matrix of left singular vectors and it's an orthogonal matrix. So U contains left singular vectors and is orthogonal. That is U transpose U is equal to U transpose is equal to identity matrix, where U is an m cross m matrix of left singular vectors and is orthogonal. Sigma over here is a diagonal matrix of dimension m cross n with singular values along the diagonal in the decreasing order. With singular values on the diagonal Furthermore, the matrix V is a matrix of right singular vectors. That is, the rows are the right singular vectors. So V transpose is an n cross n matrix of right singular vectors, and the rows of matrix V are the singular vectors. Rows of matrix V are singular vectors. V is also orthogonal, that is V transpose V is equal to V transpose is equal to identity matrix. So it's an orthogonal or orthonormal matrix. So now the question is, given the singular value decomposition of matrix A, how do we use it to minimize the objective function over here, subject to constraint that the norm of the vector with respect to which, so here we are minimizing with respect to variable. So x is a variable of the optimization. We are minimizing this objective with respect to x, where the constraint is that the norm, the delta norm squared of vector x is equal to 1. So the question is, how do we use a singular value decomposition to minimize or to minimize the objective subject constraint or solve this mathematical optimization problem? So as we discussed, once we have learned how can we minimize the objective function using singular value decomposition, we will then go back to compute the homography matrix for compute the camera calibration parameters. But here we will take this topic as a standalone topic which can be studied on its own to solve the minimization problem of this form using the singular value decomposition. So the question is, how do we use the singular value decomposition to solve the above mathematical optimization problem? So we have the following problem: minimize with respect to x norm of ax squared subject to constraint that norm of x square is equal to 1. So we can use a singular value decomposition of the matrix A and write the objective function over here. So we can write norm of ax squared is equal to u sigma v transpose x norm squared. So we used the singular value decomposition of the matrix A. So we can expand the norm over here. So the objective function then becomes u sigma v transpose x transpose times u sigma v transpose x. Recall that the L2 norm squared of an n-dimensional vector is simply x transpose x. So similarly, we have expanded this norm definition over here. So this gives us x transpose times v times sigma transpose times u transpose times u times sigma times v transpose times x, where we use the property of the matrix U, which is an orthogonal matrix, that is u transpose is an identity matrix. So this becomes an identity, and this expression over here becomes x transpose times v times sigma transpose times sigma times v transpose times x, which is equal to So we can take these two terms over here. So this is just a transpose of this term over here. So this becomes sigma V transpose X norm squared. So this implies that norm of U sigma V transpose X is squared is equal to the norm of the L2 norm, the norm squared of sigma V transpose X. So this is going to be equation number 1. Furthermore, we have in the constraint, we have norm of x square is equal to 1. So we have norm of x squared to norm squared is equal to x transpose x. So we can rewrite this as using the fact that V is an orthogonal matrix. So we can write this as x transpose times V transpose times x, where V transpose, as we learned earlier, is an identity matrix. So x transpose x is equal to x transpose Ix, and we have used the fact that V transpose is an identity matrix. So this becomes equal to norm of V transpose X squared. So this is our equation number 2. Furthermore, we can see that in both the equations we have V transpose X. So we can now define a new vector y which is equal to V transpose X. So this is equation number 3. So X becomes V times Y, where again we use the fact that V transpose is an identity. So we can using in 3 we can left multiply both the sides with the matrix V, which will provide us Vy is equal to X. So this is our equation number 4. Thus we can write the equivalent optimization problem over here. So the original problem is minimize norm of Ax squared subject to constraint with respect to x, subject to constraint that norm of x square is equal to 1, which is equivalent to minimizing with respect to y norm of sigma y squared. We are clubbing 1 and 3 to obtain this objective, subject to constraint that norm of y is equal to 1. Where we have used the fact that norm of x square is equal to norm of V transpose x square, which is equal to y. So the equivalent optimization problem is minimize norm of sigma times y squared subject to constraint that norm of y squared is equal to 1, where y is equal to V transpose x, or equivalently x is equal to V times y. So now we know that sigma is a diagonal matrix. So we know that sigma is a diagonal matrix. With diagonal entries and arranged in the decreasing order. So sigma is an M cross N matrix with non-diagonal entries being 0 and the diagonal entries arranged in the decreasing order. where diagonal entries arranged in decreasing order. Furthermore, norm of y squared is equal to 1. Thus, it follows that to minimize this objective function subject to constraint that norm of y squared is equal to 1, where y is an n-dimensional vector. So, V is an n cross n matrix and x over here is an n cross 1 vector. So, y is n cross 1 vector. And furthermore, sigma is an m cross n matrix where m is greater than or equal to n. This is our assumption over here that m is greater than or equal to n. So, assume that sigma is perhaps 4 cross 3 matrix. So, and let's assume the singular values are just we can pick any random number. So, assume like it is 4 0 0 0, then we have 0 3 0 0, and let's assume that the last column is 0 0 2 0. So, this is a 4 cross 3 matrix and y is a 3 cross 1 vector with components y1, y2, y3. So, we can see to minimize this objective function subject to constraint that norm of y is equal to 1, given that the diagonal entries are in a decreasing order, the solution to this problem would be that all the components of y be 0 and the last component be equal to 1. So, it follows using the property that sigma is a diagonal matrix with diagonal entries arranged in a decreasing order. So, it follows that the solution to this optimization problem is a vector y with all the entries being 0, only the last entry being 1. So, the first n minus 1 entries are equal to 0 and the last entry is equal to 1. So, this vector satisfies the constraint that the norm of y square is equal to 1, and furthermore, this vector minimizes the objective function over here. Thus, the solution to the original problem using 4 is x is equal to v times y, where y has all the first n minus 1 components as 0 and the last component is 1. So, it follows that x is equal to the last column of matrix V. So, x is equal to, if you write in the format of MATLAB or in the format of Python, so x is equal to v comma negative 1. If you implement this in Python, then negative 1 index over here will fetch the last column of the matrix V. So, x is equal to the last column of matrix V. Thus, the solution to the original minimization problem, minimize with respect to x, norm of ax squared is equal to 1, subject to constraint that norm of x square is equal to 1, is obtained by first computing the singular value decomposition of matrix A, which provides as u sigma v transpose, and then setting x is equal to the last column of matrix V. Thus, the solution to this optimization problem is a right singular vector corresponding to the smallest singular value of matrix A obtained by the singular value decomposition of matrix A. So, the solution to this problem is right singular vector corresponding to the smallest singular value of matrix A, which is obtained by the singular value decomposition of matrix A. So, this concludes the solution of the following mathematical optimization problem using singular value decomposition. And now we will be coming back to homography. We learned to compute the homography, it results in the optimization problem of the form minimize norm of AH squared subject to constraint that norm of H is equal to 1, where H as we discussed in the previous lecture is a vector of the components of the homography matrix, which if we could compute will allow us to compute the camera matrix K. So, this will stay in the next lecture, but so far as the solution to this mathematical optimization problem is concerned, we have learned that we can minimize this objective function subject to constraint, or we can solve this mathematical optimization problem using the singular value decomposition. And this mathematical optimization problem doesn't just occur in computer homography, it occurs in many other applications as well. So, this lecture can be used as a standalone topic for solving this kind of mathematical optimization problem for various applications.